As we continue on looking at these different transformations of functions, we begin with some slightly more difficult ones. We have an exponential here and a logarithm there, and they're a little trickier because they have some sort of asymptote. But if we think about the exponential, and we go back to the parent graph of an exponential looks a little bit like that. Again, it's just a sketch for us. And there's no reflections anywhere, so my transformed graph is going to have that same shape. Look at how these points are being changed. My x's are moving left 5 from up there, so that's going to be x minus 5. And then I have my 2y and plus 5. So it's x minus 5 and 2y plus 5. Go back to your distinctive features of the parent. We have a horizontal asymptote at y equals 0, which is important to track that. We're going to track him just like we track the points 0, 1, and 1, 2.718, or e. We're going to get just a good approximation here. So when I go ahead and transform these things, I'm going to end up with a y equals 5 for my new horizontal asymptote. This becomes negative 5, comma 7, and this becomes negative 4, comma 10.44-ish. We're just going ahead and estimating on that. So I come up to negative 5 and put my asymptote the whole way across. Go to my negative 5, 7, and put my point, and then negative 4, 10-ish is a little off my graph, which is fine. And I know that my shape should come up and just go right through. So that's why I like sketching the shape first, so I can see if my points actually line up in the right areas. The domain is negative infinity to infinity, and my range as I'm moving up the y-axis is going to start at 5, which is the horizontal asymptote, and go up to infinity. Hit the wrong button there. And from 5 on up, we don't include the number 5. If I go over to a logarithm, I know that the parent graph of the log has a vertical asymptote and has that sort of shape, but I have a reflection. So the reflection is going to take it, and since the negative sign is outside, it's going to flip it upside down. So it's going to have a shape that looks like that. And that's important later just to make sure I have the correct shape. My transformation is going to be x minus 6, comma, negative 3y minus 5. I do that like I've done all the other ones. Thinking back to the parent graph of a logarithm, x equals 0. That's going to be your vertical asymptote. 1, 0, and 10, 1 were the points that we used for now. So I transform those. X equals 0 is going to become x equals negative 6. Just run him right through that x value there. And the 1, 0 is going to become negative 5, negative 5. And 10, 1 is going to become 4, negative 8. So I put my vertical asymptote in first, going right down through there. Negative 5 is going to be down here. And 4, negative 8 is going to be down there. Those points fit with my general shape, which looks something like that. And I get a pretty good idea of what that logarithm looks like. The domain in this case is going to be negative 6. I was 1 too far over. I start at negative 6 and I go the whole way up to infinity. Start at that vertical asymptote and go right. And the range is everything, so it's negative infinity to infinity. So that's how I graph my exponential and my logarithm, track the asymptote, and then 2 points. For your examples 8 and 9, I'm going to go a little bit faster. I'm not going to write out all the ordered pairs, but I will show that my transformation here is negative x, comma, y plus 3. And then when I graph my points, I'm going to end up at 0, 3. I'm going to end up at 1, 2, negative 1, 4, negative 2, 11, and 2 down here at, let's see, 3, let me see, it would be 5. 2, negative 5. And again, you can track all those ordered pairs from the parent graph and see what this one looks like. Just want to have that there as an answer for you. The domain and range are both going to be negative infinity to infinity. Sometimes I just write really big if it's both of them. So that's one that you can practice just using the points. This one, again, I'm going to slow down a little bit on this one. For the shape, my normal shape would go like that, but I'm reflecting it twice. So if I go upside down and left, right, my shape's going to look like that. Just so I can keep that in my head as to what it should look like. I should have mentioned over here, for this one, the original shape looked like that, and the reflected should have looked like that. So just keeping that in mind. Back to the square root. Again, the filter is just going to be negative x, comma, negative 2y plus 3. You can go back to the original and see what the parent points are. I'll just show you where they end up. We end up at 0, comma 3. We end up at negative 1, comma 1. And lastly, negative 4, comma, negative 1. And those all do give me that correct shape. And I could go over to negative 9 and get a point also if I wanted to. But in this case, I'm just going to have those 3 to give me my shape. The domain is everything from negative infinity. I go up to 0 bracket because I include 0, moving from the left to right. And the range will be everything negative infinity, up through highest it hits is 3 with a bracket. So there's my transformed graphs. Again, I didn't show the parent points and how they were transformed, but you can see where they end up on those graphs. Last but not least, writing the function. First thing is to identify what function family we're in. So for the first one, we're in a square root. For the second one, we're in a quadratic. That's going to tell us what form we're working in. So for the square root, I'm going to go ahead and just put my square root. And for the quadratic, I'm going to go ahead and put something squared. And then I can add as I need to. When I look at the square root, I've tracked 0, 0, and it looks like he's gone right 4 and up 2. So to go right 4 and up 2 is going to look like that. The minus 4 in the middle and the plus 2 outside. For the quadratic, it looks like 0, 0 has gone left 2, down 3. So left 2, down 3. I now need to check for stretch or shrink. So if I remember, for the square root, normally it's 0, 0. Let me get a different color. The parent graph is 0, 0, 1, 1, and it increases from there. So what I'm going to do is take a measurement. When I go over that 1, he goes up 1. So I just check my transformed graph, and he still has that pattern. So there's no stretch or shrink. I don't have to have any sort of value in front of my square root. He's not reflected, and he's not stretched or shrunk. So my final answer is just the square root of x minus 4 plus 2. For the quadratic, if you remember, my parent graph looked a little bit like that. When I went over 1, I went up 1 again. So if I start at that vertex and go over 1, notice here I have to go a distance of 2 now, and it's down. So that's going to tell me two separate things. The down means I'm reflected, and reflected upside down comes from a negative outside. And the 2 means I have a stretch. My height of 1 became a height of 2. It was multiplied by a factor of 2, or it's twice as far as it was originally. So there's my transformed function for that quadratic. So when we're writing transformations, we just look at left, right, up, down, and then reflections and stretches and shrinks.